Okay, welcome to the second part of Chapter 7 lectures. We're going to be talking about intelligence testing. So, in our last lecture, we talked about the various theories of intelligence that were presented over the years, but now we're going to focus more on the different testing methods for testing intelligence. So, intelligence tests were created to quantify a person's level of intelligence. Now, in order to do this, we have to be sure that tests are actually measuring and accurately measuring the thing they're supposed to measure, which in this case is intelligence. So, just kind of a real world example of how measuring can go wrong. If you were to step on your bathroom scale, for example, you want to know beyond a shadow of a doubt that the scale is actually measuring changes in weight, not some other outside factor, right? Otherwise, you would have no confidence in that scale, in that thing that is measuring your weight. So the same goes for intelligence tests. In order to have confidence in the test, we have to ensure that it's accurately measuring what it is supposed to, which is intelligence. And there's a couple of ways that we can ensure this through reliability and validity measures. So that's what we're going to talk about next. So, what is validity? This refers to the ability of a test to measure what it was designed to measure. Okay, so does a scale measure your weight? Does a ruler measure the length of something, right? So we're making sure that this test of intelligence, these IQ tests or intelligence measures, are actually measuring intelligence, because if they're not, then the results are just not useful to us. So there are three different types of validity when you're considering validity of a test. The first is content validity. So this is the degree to which the actual content of a test, so the items on a test or the problems on a test, they represent the area they're intended to cover. So just an easy example, if you're taking a math test, it should consist of a bunch of math problems, right? It shouldn't have, say, a bunch of art pictures, right? Or impressionist pictures all over the exam. If it's a mathematics test, it should have math problems, right? So in this case, we're looking at intelligence. So the content of that test, of the intelligence test, should reflect the overall area of intelligence, or what we're trying to measure. Then we have what is called construct validity. So, this is the extent to which there's evidence that a test measures a particular hypothetical construct. So, essentially, the measures from the test, are they consistent with theories of intelligence? So, we spent the entire last lecture talking about the various theories of intelligence. So, do these tests or do the results of these tests actually match what those theories are saying? If it's, if the results of this test are way out in left field, no theory has ever looked at, considered, or talked about it, you might not have construct validity, right? We want to see some similarities with the measures that we're getting from the test that also adhere to the theories that have been presented on intelligence. And finally, we have what is called predictive validity. So this is the ability of the test to predict future performance. Will your performance on one test predict how you do on the next test? Then we have what is called reliability of the test. So we have validity, which was split up into three parts, and reliability. Excuse me, I'm going to sneeze. So sorry. Okay. So the reliability of a test refers to whether or not the test yields consistent results, okay, across multiple takings of that test. So do individuals score the same each time they take the test, or at least very close to their score every time they take the test? This can be, the way this can be measured is by comparing scores from two administrations of the same test. So the individual takes the same test twice. And if the test has high reliability, which is what we want to see, we would expect to see a strong positive correlation between the two scores. Okay, so 1.0 would be perfect correlation, right? You would see the exact same score on both tests that they took, which you might not see have a perfect correlation. Typically, we do not, but we do expect to see a pretty high correlation value if the test has reliability. Okay. But in order for a test to be a good measure, we have to have both. It has to be both reliable and valid. Both of these things are prerequisites to have an accurate measure of something, in this case, intelligence. So if the test is reliable, you're able to score the same across multiple tests, but it doesn't actually measure what it is supposed to measure, then it has no validity, right? So you might have one without the other, but it wouldn't meet the standard for being a successful test, right? It has to have both. Okay, and you might have validity but no reliability. But again, this doesn't meet the standard of a good measure of whatever it is you're measuring, which in this case, we're looking at intelligence. You have to have both reliability and validity of the test. Some other things to think about as we discuss intelligence testing is whether or not IQ can even accurately be measured through the act of test taking. Because if you think about all of the other variables that might influence your performance on a test, what if you have test anxiety? Um, this can certainly influence your performance, right? Maybe you don't have motivation to even take this test. Maybe you're being forced. Typically, when we do research, right, we can't force people to take a test, but you never know. Maybe you're in a class and the teacher says, we're all going to take this survey. So you might not have motivation to even do the test. Maybe you have previous test experiences that are helping you on this test, right? So there's all these extraneous variables. We talked about this in week one when we talked about research methods and how we have control over the results that we get. Well, individuals are bringing in any number of extraneous variables with them when they're taking a test. These cannot be controlled for by the researcher. So when we're looking at measures of a test, we have to kind of be skeptical of them because, test taking in and of itself brings in all of these other variables that we need to account for when we're looking at the results or the measures that they produce. There are also many biases that can be associated with tests. So, for example, what if all of the questions on the test are related to a specific culture? Quite typically, on an IQ test that's delivered in the US, it might refer to various things in our own culture here in the United States. But someone from another culture, another country, they're probably going to score quite poorly, not necessarily because they're not intelligent, right? It doesn't really have anything to do at that point with their level of intelligence. It's only that they're not familiar with the topics being presented in the questions, right? They don't know what these items are referring to because they're not from our culture. Same thing with language. If you have someone whose English is a second language, maybe they don't speak it or read it that well, you give them an IQ test that's all in English and they will probably score poorly. Again, this does not reflect their intelligence. All that tells us is that they can't read and write in English very well, right? So we have to keep these sort of test biases in check and in mind when we're considering these measures. Are the individuals taking these tests coming prepared to actually take the test that they were given, right? Or are there these biases of the test that are influencing someone's performance? So keep this in mind as we go through intelligence tests and measures, that whenever we're talking about them, you have to keep in mind, that results are going to vary, especially if you're dealing with individuals that the test is not biased towards, right? Which means the test would be biased towards English speakers when it's written in English, right? And biased against those that don't speak English as a first language. So you need to keep that in consideration at all times. Now, I also posted a TED Talk video. It's very short. I think it's like 5 minutes. I posted two different ones, but this first one, it's very short and it sort of talks about the history and the darker side of IQ tests, how they've been used throughout history in various ways they were never intended to be used that way. So I'll warn you that some of the information and the facts that they give in that short video are a little disturbing, especially if you've never heard them before, if you weren't aware that IQ tests were in fact used for these things. So just be forewarned. You don't have to watch the video if you're somewhat sensitive to those things. You won't be tested on it. I just thought it was a really nice sort of brief summation of the history of IQ tests and sort of what can happen when they're used incorrectly, right? And why we need to be very careful when we're using them. So keep that in mind when you watch that video. Okay, so here's two questions I'll show you, and I'll ask you, are these fair questions to ask? And why or why not? So I'll just let you sort of look at question one and question two. Well, unless you speak German or unless you speak French, you have no idea what each of these questions are saying. So for the demographic of English speakers, these would not be fair questions. So it's the same when we're giving tests to someone who speaks German, right? But the test is in English. Again, the results of those tests would have nothing to do with their intelligence. So this is what I'm talking about when I'm talking about test bias, right? If I gave you as an English speaker a test that was all written in German, it's not a test of intelligence anymore. It's a test of how well you speak German, right? So just keep that in mind. These tests only reflect intelligence scores if the individuals coming into the test have the prerequisite skills to answer these items, right? So just something to keep in mind, just to give you an example of what it would be like if you came in and took a test that wasn't in your own language. Okay, so let's get into all the different tests that have been developed over the years. So Alfred Binet was the first to develop an intelligence test. Um, and he used this test to identify children who were in need of remedial education. So maybe those children who were perhaps falling behind in school or academically, and they just needed some extra support. Binet gave these tests to groups of typically developing kids, and each group was of the same age. So he had a group, for example, of 5-year-olds, a group of 6-year-olds, a group of 7-year-olds, and so on. And what he would do is he would assign a mental age based on the child's score. So what he did was he looked at those problems that most of the kids in each age group could solve. So for example, he would assess the problems that most 9-year-olds could solve. And if a child could solve all of those problems, but then maybe failed to pass subsequent problems that 10-year-olds could solve, they would have what he called a mental age of 9, right? So they're accurately answering those questions that are accurately answered by most 9-year-olds, and thus a mental age of 9. Typically, those children with intellectual disabilities would have a lower mental age than their actual chronological age. So maybe a 10-year-old, right? That's their chronological age, their actual age. After taking this test, we might see that they have a mental age of a 7-year-old, right? They can only answer those questions that most 7-year-olds can answer. But when they get up to the higher aged questions of 8-year-olds, 9-year-olds, they can't answer those accurately. So through this, he developed what is called the Binet-Simon scale. Now, he developed the scale with one of his students, whose last name was Simon. So that's why it's called the Binet-Simon scale. And this was the very first test to measure intelligence in any way. But it only measured based on mental age. So it's only taking into consideration that result of the test's mental age that he was giving. And this can kind of be an issue. For example, a child whose mental age is 7 might be problematic if their actual chronological age is 10, right? Because that shows us that they're behind. But what if the child's mental age is 7, but their chronological age is 5. They would be considered advanced, right? Because they're answering questions beyond their chronological age. But the Binet-Simon scale didn't account for these differences. It didn't account for maybe being ahead of or um, advanced in terms of your mental age. It only looked at mental age alone, your mental age score. It didn't then compare that score to where you are chronologically in age. So in 1916, a professor at Stanford University, Louis Terman, he adapted the Binet-Simon scale to assess for this relative intelligence, right? The mental age, but compared to your chronological age. So we can see if you're actually ahead or behind of where we think you should fall. So rather than only taking into account one of these factors, he adapted the scale to get a relative score in terms of IQ. So this is the calculation of the Stanford Binet scale. So this is the one by Louis Terman, the one that he adapted. CA is going to represent chronological age, and MA is going to represent mental age. Okay, so that's the age of the children with comparable mental abilities. Now, if a child scores a 100 on a test, their mental age is going to probably exactly match their chronological age, right? So they score 100, their mental age is 9, and their chronological age is 9 as well. So here's an example of this. So if a child is 9 years old in chronological age and scores a 9 in mental age, their overall IQ would be 100. So here you have 9 over 9 times 100. It's going to equal 100. So that's their IQ score. Okay. Whereas if the child's chronological age is 9, but their mental age is 8, right? So their mental age is slightly behind their chronological age. Their overall IQ is going to be 88.9. Okay, so now you see how we're taking into account not only their mental age, but also their chronological age as well. So it's slightly behind that 100. So 100 is kind of where we want everyone to be. That's sort of like the average score. And then we see how far below or how far above children score. And again, we can account for those who are ahead. So if the child's chronological age is 9, but their mental age is 11, their overall IQ score would be over 100. It would be about 122.2. So his measurement was able to look at the sort of relative IQ score, taking into account both mental and chronological ages. And here's just an example of a Stanford Binet intelligence scale that might be given to a 10-year-old. All of these scales given to any age groups have same categories, but the measure in each category differs depending on the age of the individual taking the test. So you're going to have things like vocabulary, block counting, abstract words, repeating digits for a 10-year-old. And then you see the specific questions in each of those categories, right? So for a 10-year-old in the category of vocabulary, for example, they're going to correctly have them, or they're going to have them define 11 words from a graded list of 45. They have to correctly define 11 of those words to fall into the mental age score of 10, right? And you can look at all of these examples that way. Same thing. They're given abstract words. A 10-year-old should be able to correctly define 2 of the examples from the 4 that are given, right? So if they're given pity, curiosity, grief, and surprise, in order to fall in the mental age score of 10, they should be able to correctly define 2 of those things. Okay. And then we have David Weschler. So he came up with the Adult Intelligence Scale. He developed this, the WAIS. And this is the most widely used IQ test in the USA. It has 10 unique subsets. So we have 3 measures of verbal comprehension. We have 3 measures of perceptual reasoning, 2 measures of working memory, and 2 measures of processing speed. Verbal comprehension, this index reflects an individual's ability to understand, use, and think spoken language. Okay. It also is supposed to measure how well or how much knowledge you've acquired from your environment, and also measures retrieval from long-term memory. So information that you're retrieving from your long-term memory, such as vocabulary, right? Definitions of words. The perceptual reasoning index reflects an individual's ability to accurately interpret, organize, and think with visual information, right? So how well can you visualize something? So this sort of measures more nonverbal reasoning skills, right? Thinking that's more fluid, you're sort of solving things that are new or novel situations, like fluid intelligence is used here. Then we have working memory index. So this reflects an individual's ability to take in and hold information in immediate awareness. And then you perform a mental operation on that information. So essentially, you're being given a problem and you're solving it mentally, right? So here we're looking at the manipulation of number operations, maybe digit span, can you remember certain digits and sort of do mathematical equations with them, and so on. And then we have the processing speed index, and this reflects an individual's ability to process simple or routine visual information quickly and efficiently. So it's measuring your visual and motor speed. How fast can you react to something? When you see something, how quickly can you respond to it? Things like that. This also measures processing speed, also measures your ability to recognize and find patterns in things. And your IQ score is determined by your performance on all of these subsets. So it's the average that you're getting across all 10 of these measures. And then, of course, he also ended up developing one for children as well. So, all of the scales we've talked about up until this point, up until David Wechsler, are largely focused on children. So he was the first one to sort of come up with an adult intelligence scale. And then he did develop that scale into one that could be used with children. And it is the most widely used IQ test in the USA. So let's look at some problems as to what this would look like. So which number should come next in this series? And I'll just give you a few moments to sort of look at these. So the answer here is C. Okay, it should be 10. And here's why. If we look at the numbers, 25 minus 1 is 24. 24 minus 2 is 22. 22 minus 3 is 19. So as you can see, the number we're subtracting from each of these increases by 1 every time. So by the time we get to 15, we know we need to subtract 5 from that number, and thus the answer is C. So this is a mathematical measure on this test. How about this problem? So here the answer is C. So this item looks at pattern recognition. And to get this answer, you not only have to look at the position of the shaded box, but also the direction the arrow is pointing in. So A and B are pretty obvious that those aren't the correct answers. That arrow is not in line with the shadowed box, but C and D are. So then we have to look at what direction is the arrow pointing, and does it correspond with how the arrow rotates with the first 3 boxes we are shown. Here's another one. Which of the sets of letters can be arranged into a 5-letter English word? So I'll give you a second to kind of look at all of these. And the answer here is C, and the word that it forms is snarl. So this item is a verbal measurement, obviously, because we're looking at jumbled letters and forming a word. And one final example, this one is figure out which is the odd one out among these images. Now I have to be honest, this one took me a minute to sort of figure out when I was looking at all of these examples online. So I'll just give you a second. And here the answer is D. Now the reason being, if you rotate that first image of A, the one you see A, if you rotate that image clockwise, you get A, B, or C. But in order to get image D, you actually have to flip the image completely. It's a mirror image, so it doesn't fit, right? It's the odd one out. The other three you can get just by rotating the image clockwise. So this item measures pattern recognition. So those are just a few fun examples of what you would see on a Wechsler intelligence scale test. Then we have another test developed by John Raven in 1936. So he developed a test that presented a matrix with related elements. And one of the elements is going to be missing. Now, the individual taking the test has to choose the missing element out of a multiple choice option. So it's a multiple choice test, and they have to select which one best fits the element that is missing. This test does not rely on language, literacy, or any kind of cultural knowledge, but it only measures abstract reasoning, abilities of independent and general knowledge or previous experience. So again, this test is going to measure fluid intelligence because you're using fluid intelligence to solve new or novel problems, right? It's not pulling from general knowledge in this sense. So here's some examples, which would be the missing piece. This one is fairly obvious. It's option 6, right? So if you plug that box into the missing part of the one above, you'll see that it fits perfectly. How about this example here? I think everyone would know the missing piece here is going to be option 4, right? So that piece, if you were to mentally move it into that blank spot, you'll see that it fits well. How about this one here? The missing piece here is going to be option 8. Okay, so that fulfills the missing part. And this final example is going to be option 3. That would be the correct one that would fill the blank in. So these are just some examples of what you would see on Raven's progressive matrices tests. And when you're being given the tests, of course, these get progressively harder and harder. So they start out sort of easy, and then they get harder and harder as the test goes on. And as you can tell, these are more abstract items than things like word recognition or number memory and things like that. So like I said before, this is looking at abstract problem solving abilities. Okay, let's talk about IQ, or the intelligence quotient. That's what IQ stands for, in case for anyone who didn't know. A person's IQ score is determined based on how they perform relative to others in the same age group. Okay, so that's what we're looking at when we're looking at IQ scores. It's comparing you to the average of the group of people in your same age. And thus, IQs are judged using a standardized sample, so a standard score for the group. Now, I'm not going to get into too much of the nitty-gritty statistics here, but I am going to show you how to look at a normal distribution of scores and calculate where someone's score may fall within that distribution. So whenever we're looking at scores of IQ, the mean or the average of the group is 100, and we have a standard deviation of 15. Okay, so one standard deviation equals 15. Here is the normal distribution of scores. This is what a normal bell curve should look like. We have about 40% of the population scoring 100, right? So that's what we call the average or the mean of scores. And then you see scores that deviate from that mean, right? And in a typical bell curve, you would have sort of this very equal distribution of scores above the mean and scores below the mean. If you've taken any kind of statistics course, this typical bell curve looks very familiar to you. But even if you've never taken a course like that before, all you're looking at is the average is that top point, and then you have an equal amount going to the right of the x-axis, which would be above the mean, and an equal amount going to the left of the x-axis or down the x-axis, which would be below the mean. The standardized test scores, this is represented by the letter Z, tells you how many standard deviations a score is from the mean or the group average. So when we're looking at a normal distribution of scores, like we did on the previous slide, 68% of those scores are going to fall within one standard deviation of the mean. 95% of those scores will fall within two standard deviations of the mean or the group average, and 99.7% of scores are going to fall within three standard deviations of the mean. So the greater the value of Z, that's the standard deviation. So 1, 2, 3, those are values of Z, the farther away the test score is from the mean. Okay, so if you have one standard deviation from the mean, that's less of a deviation than three standard deviations from the mean, right? Or from the average of the group. So here is the normal distribution again, where you can see those percentages we are talking about. So the group average falls right in the middle point, which is that middle line going straight up from the center. So that's the group average, which is 100. You've got 34% falling one standard deviation below. So that's the red section to the left. And you've got 34% of the population falling one standard deviation above the mean. So it's the red section to the right of that straight line in the middle. Then you see the yellow areas are now included. So for two standard deviations above or below the mean. And finally, you would include the green part, which falls three standard deviations above or below the mean. So let's look at some practical applications of how you would do this. And this is how problems will be presented on your exam, okay? So let's say we have an IQ score of 130. So that's my score. The mean or the group average, as we discussed before, is 100, and one standard deviation equals 15. So how do we figure this out? We want to know how many standard deviations my score of 130 is away from the mean or the average of 100. So we start at 100 because that's the mean, right? That's the average. We know one standard deviation from that is 15, right? That it tells us that. We know that. So to get our score of 130, we would need two standard deviations, right? 15 plus 15 is 30. You add that to 100 and you get your score of 130. So my score is two standard deviations above the mean. Here's another example. What are the standard deviations for each of these scores? Okay, let's talk about this. The first one, A, is 100. Now, if we look down at the image, you can find the score of 100 right in the middle. That's the mean. You see that it lines up with the 0 on the x-axis. So a score of 100 is 0 standard deviations from the mean, right? It is the mean. So that's the mean score, 0 standard deviations from the mean. What about 145? If you have a score of 145, again, recall, standard deviations are in increments of 15. One standard deviation is 15. So we can look at a score of 145 and see that it falls 3 standard deviations above the mean. So you can do this a number of ways. You can look at the picture that I've posted and just see that the score of 145 lines up with a +3 on the x-axis. You have 3 standard deviations. Or You know that one standard deviation is 15. So if we have 145, that's 15 times 3, right? So 3 standard deviations. And hopefully from that you can figure out C, D, and E on your own. Okay, so you can do this either by doing the math or by just looking at the picture that I've given you. How about this question? Your IQ score is 2.5 standard deviations above the mean. What is your score? Now, again, you can either use the image to figure it out, or you can use the math. I'm going to use the math just to explain it one more time, how you would do this, but you can also look at the picture below to figure this out. If one standard deviation is 15, then 2.5 standard deviations will be 37.5, right? Because we have 15 plus 15 is 30, and then we have 0.5, 2.5, right? Which would be 7.5. So 37.5. The mean is 100. We know this, right? That's the average score. So what we do is we add 37.5 to 100. That's 2.5 standard deviations added to the mean score of 100. And so your score is 137.5. And finally, what if your score is 1 standard deviation below the mean? So now we're going to go the opposite direction. You're below the mean. We know 1 standard deviation equals 15. So again, we're talking about falling below the mean. So we subtract 15. We subtract 1 standard deviation away from the mean, which is 100. And by doing that, we get a score of 85. And that is all I have on the lecture on intelligence testing. You'll find several questions on the remainder of these slides that will sort of give you an idea of questions you'll be seeing on your upcoming exam.